So let me check if is the screen visible, please?
Oh, sir, it is not visible.
Screen is visible. Somebody is saying screen is visible. Yeah, I have opened the file. Is the screen visible, please? Hello.
Sir, actually, there is a share screen option, sir, which is in green color. Did you press that?
This one?
Sir,
Middle of the window, sir. There is a shared screen option in green color.
Yes.
Press
Yes,
that,
I
sir.
have pressed share screen. Yes, I have done that. Enable remote control of for all applications. Is that what I had to press?
Sir, press on the arrow mark that is there, and
Six options. Enter full screen, scale, enable the remote control of all applications, share screen.
press on screen so that you can share the one which you are opening.
Yeah, share screen is what I have pressed. Silent system notifications and side-by-side mode. Is that what I have to choose?
Sir, open the document, sir.
Share screen I have opened. Oh yeah, I have opened the document also.
Yes, sir.
No visible. No, it is not visible. Can I email this to one of you?
Yes, sir. You can email us. You can email it to us. Bharati Vignan Mandali mail, sir.
The same Vijnan Mandali mail. Okay,
Yes, sir.
excellent. Has it been received, please?
So we are checking. We are checking, sir.
Yeah.
Yes, sir, we have received it.
How do I have control on that? Can you share it?
So you can just say next slide and we'll actually change the
That
slides.
will be terrible. It would have been easy actually. Oh, somebody is saying, oh, oh, yeah. Okay, excellent. Now screen seems to be visible, and yeah, the screen is visible. And good morning to all of you. Can I get started, or what's the plan of action?
Good morning to all of you and good morning, sir. Today we are welcoming Professor BSV Patnaik, sir, for this FDP program for the day 3. Professor BSV Patnaik, sir, is a professor at IIT Madras, received PhD from Indian Institute of Technology, Madras. He guided 6 PhD scholars, published 53 papers in peer-reviewed journals and conferences. He is a lifetime member of Indian Society of Heat and Mass Transfer, National Society for Fluid Mechanics and Fluid Power. His research interests include computational fluid dynamics, CFD tools for FSI, microbiofluid flow systems. I welcome you, sir.
Thank you, and good morning to all of you. And can I get started? Am I audible in the first place?
Yes, sir, you are audible, sir.
Okay. So I request all the participants to ask questions as we move on, because the purpose of a talk like this is by and large to have more of discussion rather than giving a one way type of lecture. So please feel free to ask questions. If I know the answers, I will be happy to respond. If I don't know, we can always go to some real experts who can do better, and we'll get the answers for you. No big deal. Okay. So let me at the outset tell you that turbulence is pervasive. It's everywhere. It's there when we breathe. It's there when we sort of, when we want the pollutants from all the vehicles to get out of the roads, and then ensure that we are not asphyxiated and so on. It's also there when there is fluid ejection from the ventricles and through the aortic valve and goes into aorta, the heart where the blood is pumped in the systemic circulation, and then it's there everywhere, literally. Only thing is, no, don't go that forward, please. Unless I tell you, don't go forward. Okay, just still go back. So
yes,
this is the outline. So
okay,
don't give the control to me so that I take care.
Actually, whoever shares the screen, he will be having the control, sir. Who will go according to you, sir?
Yeah, you just listen to me. Just when I say next slide only, you move to the next slide.
Yes, sir. Thank you.
Okay. So turbulence is pervasive, and then we want to look at this serious subject of turbulence, and it's typically offered as a full-fledged course, and what we are trying to learn in, I'm not sure, 1.5 hours or 2 hours, whatever time you want to want to face me. I'm happy to just sir, background noise from where? Coming from where? From me or from other source? Uh,
Sir, it is from your location, sir, somewhat.
my location. Uh,
Sir, if possible, can you have earphones, sir?
I can have earphones, but I don't have a microphone. Am I audible now?
Yes, sir.
Okay, okay. Then I have to understand that I have to speak into the microphone. There is a microphone right on the laptop, so I have to speak into that. That's where the problem is.
Okay,
Okay,
sir.
I'll do that. I'll do that, and then one of the most important things is to understand in the context of turbulence, to understand the right length scales, velocity scales, and time scales. If we can understand, these length scales, time scales, and velocity scales, which will be spanning over a wide range of, in terms of, the order of magnitude. They'll be spanning from, small scale eddies all the way to large scale eddies, and then we need to understand that, and therefore all our engineering calculations would become straightforward and easy. So the idea is to just give you a brief overview of turbulence, some pictorial view, and so that you understand more in terms of pictures to start with. Not too many pictures, but the real crux of this discussion happens when you think of something called the Reynolds averaged Navier-Stokes equations. If you're thinking of, I'm not sure how many have background in Navier-Stokes, but if you're familiar with Newton's second law of motion, Newton's second law of motion, as we know, is F equal to ma. The sum of all the forces acting on an object is essentially mass times the acceleration. So the same thing is translated in the context of fluids, because you cannot pinpoint a certain mass, you cannot pinpoint what is an acceleration associated with trillions and trillions of particles present within the fluid mass. So it's extremely critical that F equal to ma has to be translated into a control volume based formulation, and then one has to really bring up. So everyone is getting disturbance. I'm not getting any disturbance, but is it audible? There are some people who are saying there is disturbance.
Yes, it is audible, sir, but echo is coming, sir, because
Yeah.
speaker is on. Same voice will be coming back again. Echo.
Oh, so if I am a little far away, uh, so I think there is a fan. Yeah, there is a fan. That fan is not. Is a fan noise is the one that's responsible. So it requires an auto cancellation or some filter that's able to.
Sir, if possible, you can have earphones. It will be okay, sir.
Correct, I have earphones, but earphones doesn't help. You need a microphone.
Okay. Okay.
Earphones doesn't help. Only microphone helps.
Yes.
So. Okay, just give me a second. Yeah. No, I could not find any microphone. If I'm coming very close to this laptop-based microphone, and there is an echo, and if I'm a little far away, then there is a problem with the voice reaching the microphone. So let us quickly see. Maybe earphone has a microphone. Every earphone need not have a microphone, right?
Sir, yes, sir. Yes, sir.
Yeah.
Okay, sir. You can go on, sir. It's okay.
Yeah. We'll go on because there is no other quick choice. I have told my office.
Okay, sir.
It is the example of effect of turbulence. No, acoustic. Acoustics is a different game altogether. So a pressure disturbance travels, and then it's not the physical movement of any particles. In the context of turbulence, it's the physical movement. Okay. Acoustics is influenced by turbulence, and noise is influenced by turbulence. But then turbulence itself is not noise. So what is generated, etc., will create noise.
Yes.
Keeping that aside, let us quickly, look at what aspects of turbulence we plan to cover. In this slide, I have given the overview. We want to especially discuss Richardson's cascade, and breathing of air is also turbulence. Yes. You are muted. Alt A to unmute your microphone. You are unmuted by the host.
Oh, sir, you are okay, sir. You are audible.
So to just give you an idea, there is something called mass conservation equation, momentum conservation equation. We also need to look at statistical averaging route to Navier-Stokes. And then, of course, turbulence modeling in the process needs to be understood how to model turbulence in the context of statistical averaging. Okay. So if we look at the ideas associated with turbulence, the standard engineering style is to how to perform our engineering designs. Go to the next slide, please. Go to the next slide. Yeah, you can see a large number of engineering applications which are impacted by turbulence. You can see that the top left corner is an internal combustion engine. You want the fuel and air to mix extremely well, and turbulence facilitates that. And because of turbulence, we are able to have extremely well mixed air-fuel mixture, which can be burnt completely. Otherwise, if there is unburnt fuel, naturally, the engine will be highly inefficient. Engine is likely to belch lots of pollutants into the atmosphere and so on. We certainly require complete combustion. Turbulence aids that. If you're thinking of flying machines in air, flowing submarines on the water, you need to understand aerodynamics. You need to understand hydrodynamics. Turbulence completely controls both aerodynamics and hydrodynamics depending on the situation. And you think in terms of drag reduction of vehicles, and think in terms of vehicles which are, for example, wherein you want to look at Formula 1 race cars kind of situation. You just do not want to reduce drag alone, but you also want to make sure that lift to drag ratios are also within the favorable limits. Turbulence certainly controls that. In the right bottommost picture here, we can notice that the turbulence generated what is called the vortices which are produced by the wings of this aircraft can easily kind of twist another small vehicle behind this. So that's likely to cause a very serious, there is turbulence associated with the generation of these strong vortices, which are likely to completely twist any smaller vehicles behind it. So there is a time gap between any two takeoffs and so on. But right now we are not really concerned about takeoffs and landings because most aircrafts are completely grounded at the moment. Okay, so I think you cannot start share screen while other participant is share. Can you stop sharing so that I can share now? Hello?
Okay, sir. Okay, sir.
Yeah, please stop so that now I can see this button. I will have better control.
Okay, sir.
Yeah, you stop it, let us see.
Stop it, sir.
Okay. Yeah, I can even use a whiteboard, share, yes. I can use, oh my God, now I got everything. Okay, good. Good, at least I have control. Is it visible?
Yes, sir. It is whiteboard. Whiteboard is visible.
Okay. Now I have got everything. Yes.
Sir, my slides are visible.
Yeah, slides are visible. Excellent. Thank you.
Thank you, sir.
So I can. Okay. So the brief outline is what this is what I was mentioning, and some applications related to aerodynamics, related to complete combustion associated with the complete mixing. Turbulence enables complete mixing very quickly, and these vehicles, both airborne and waterborne vehicles, are completely designed with turbulence as the main aspect that needs to be looked at, because the lift to drag ratios and the corresponding propulsion, etc., is completely controlled by turbulence. So some of the common characteristics of turbulence, some features that most of you are familiar will be: turbulence is random, chaotic. These are all essentially features of turbulence, and small scale random vorticity will be generated, and then it's a phenomenon of high Reynolds numbers. It highly dissipates energy, and it's a continuum phenomenon. It's of course three-dimensional, and so on. One of the most important things that one should look at is how do I define turbulence? This will be one of the serious questions. If somebody is asked how to define turbulence, it's extremely important that we have to sort of appreciate this is how turbulence can be defined. Maybe some participants can respond how they think turbulence can be defined, and if some of you think, one of the earliest experiments, of course, I grew up by using Reynolds pens. I'm sure, nowadays kids may be using different other types of pens, and Reynolds was the early pioneer. Of course, his grandsons and others have made quite a bit of money with the success associated with Reynolds pens. Osborne Reynolds, I mean, there are many Reynoldses, of course. His entire family tree is, the Reynolds die experiment is quite popular. And the old man, you can see one of those, early experiments was to release a die and study the flow of fluid and the corresponding die which is released somewhere along the center line. You can see a tube here. So there is a bell mouth entrance here, so that the fluid is accelerated, but at the same time quietened through the process of acceleration, and no chance or no opportunity for disturbances to develop further. And once along with that, there is a needle like colored fluid is released along with that, and that colored fluid, how is it getting released within the tube? Is the colored fluid being layered? For example, if the flow velocity associated with this is very small, the corresponding flow will have a straight line, meaning you will have what is called layer by layer kind of flow. This layer by layer type of flow is what is called a laminar flow. And in the context of, up to some point, it is able to suppress any disturbances, but after some time, it's not able to suppress disturbances if the velocity is little high. The same dye would come out through the needle continuously and more like a line along a single line, but it completely fills the entire tube. And this kind of a filling, if you look at one of those striations, there is a possibility that you will have some kind of a sinusoidal structure, more like a sine wave kind of up and down kind of motion. You can also notice that, this is what is a typical turbulence associated. This turbulence will have certain features. It is unlike diffusion. You have a large scale mixing. Convective processes completely dominating this. In early 1883, what Osborne Reynolds found was about Reynolds number of 2000. If there is any special effort to quieten the flow, it's possible to have the Reynolds number around 2300. This is the kind of standard textbook kind of a number that most of you would have learned in a standard fluid mechanics course. But please notice that, till what Reynolds number can you control laminar? It is a very good question to pose, and then can you make some guesses till what Reynolds number can we have laminar flow? if there are controlled conditions, it's possible to control turbulence all the way in a pipe flow, of course. When you have flow through a pipe, the Reynolds number corresponding to the situation that we are talking about is typically defined something like this. Reynolds number, RE, Reynolds number RE is essentially rho, the density, because I cannot use, and some length scale, in this case diameter, divided by the kinematic viscosity. Kinematic viscosity is, of course, typically mu. Mu is kinematic viscosity. Mu refers to kinematic viscosity, and D, of course, is a length scale, and of course rho, as you know, is density of the fluid. And kinematic viscosity can also be thought of as dynamic viscosity divided by, I'm sorry, there is something more missing. There is velocity. Sorry, there is a mu here. Completely missed. Velocity is incorrect. I'm sorry. It is dynamic viscosity. Mu is kinematic viscosity. Mu is essentially mu by rho. So you can write as rho Vd by mu, or mu by rho can be, or you can also write it as Vd by mu. Okay, rho Vd by mu is the standard version that most of you would have come across, and Reynolds number is somehow came to be one of the characterizing number and our non-dimensional grouping that characterizes either the flow as laminar or turbulent. Okay, so going beyond this, we can just quickly say that, okay, look, this is how a laminar flow or a layer by layer flow would look like in a pipe flow. You have a nice fully developed velocity profile. For example, when it is moving layer by layer, you can see that this, even a small chunk of fluid from here will not be jumping into this and trying to equate the momentum between the two layers. Whereas if the flow is jumping up and down, for example, a fluid chunk from here will jump into a layer above. From above, another small fluid particle will jump below. And in the process, one of the serious questions is what will happen to this particular parabolic velocity profile? It is looking more like a parabola, right? So if there is a flow through a tube, a typical velocity profile is a parabolic velocity profile. One can see that there is a no-slip boundary condition associated with the surface. Surface velocity will be 0 because the fluid in contact with a solid boundary which is not moving will have the velocity of that boundary. Okay. So you can notice that you have exchange of momentum across different layers of this fluid, and therefore you can notice in the context of turbulent flow, this is in the context of turbulent flow, you have essentially in the context of turbulent flow, you can see that you have a, there is a chunk of fluid jumping from this to this, this to this, this to this, and back and forth. So therefore, if you look at the velocity profile across this particular cross-section, you will see a almost flat velocity profile. Okay, very close to the wall, you have a much steeper gradient. The word steeper gradient is responsible for identifying what is called, what is the wall shear stress. The wall shear stress would shoot up dramatically in the context of turbulent flows. You can see that on the surface of the wall, you have a 0 velocity or a no-slip boundary condition. A little away from the wall, you can see that the velocity is very high. So as you go towards the center line, the velocity drastically increases very close to the wall, unlike the laminar flow. You can see that in the context of laminar flow. You have a certain velocity jump and the velocity gradient is not steep. Whereas the context of, if you zoom this particular region very close to the wall, you have a very steep gradient. Even that steep gradient, of course, will have a certain haphazard, if you look at one velocity signal, if somebody is using a velocity probe and measuring at different sections, different stations all along this line. Yeah. Anything? Hello. Any questions in between? Can we go forward? Okay.
Yes, sir. Yes, sir.
Yeah. We can see that there is certain randomness, and if you have several such random, for example, we can quickly say that, okay, I have another velocity profile, something like this, little not very nice, but another velocity profile, if I measure, it will be like this, and so on. If you average all the velocity profiles, you will get a very clear flattish velocity profile, and you can notice that this velocity profile is going to be almost flat in the middle, almost 90% of this cross section. Only very close to the walls, very close to this surface, you will have a very steep gradient. Let us move on beyond this. So the key concern is you have smooth flow, layered flow called a laminar flow. You have highly erratic, random, haphazard flow called a turbulent flow. This is what you see in the context of a jet coming out of a faucet. Whereas if you go to the tube, a circular cross-section, the tube like this, and if the flow inside is laminar, if the flow inside is turbulent, this is the nature of velocity profile. A paraboloidal profile is what you will see. Whereas in the context of turbulent flow, you will see something like this. It's extremely important to understand this for very serious reasons. Because the nature of engineering designs would drastically be different if the flow is laminar or turbulent. If the flow is laminar, you have the pressure drop corresponding to facing the frictional resistance associated, and those frictional resistances will be drastically different if it is laminar flow versus turbulent flow. Some of you may be familiar with something called Hagen-Poiseuille flow. One can quickly say, okay, you have a velocity signal, and that velocity signal can be thought in terms of, if I measure a velocity signal, I have x-axis, on the abscissa, I have the time, I have on the y-axis the corresponding velocity signal. How is this velocity signal varying? Will it vary like this if I keep on measuring? Or if I measure once more, will it vary like this? Think of this kind of variations as temperature variations within the same day of a particular day. Of course, the day temperature will not be like this. It may simply go up to the noon, and it may come down. Another day, if you think, if it is highly turbulent locally, it may be something like this. Another day, it could be highly, very different. But if you look at the statistical average of all these different day temperatures in the month of May, let us say, they all will give you, in a statistical average sense, it will give you a nice, predictable profile. Maybe the individual variations are not predictable, but the statistical average version of this, meaning if I do the averaging of all this, different signals, for example, if I do a statistical averaging of all the signals that I specified here, I may end up getting a very nice straight line looking signal, something like this, as a function of time or as a function of space or whatever. So it's possible that statistical averaging is one of the routes to conquer turbulence, understand turbulence, perform predictions, do modeling, and so on. So let us try to quickly, look at some more pictures. Okay, you have a jet issuing into some kind of a colored jet coming out of a nozzle. There is a small nozzle because of an orifice. There is a small hole essentially. You have fluid, coming out, and then it is a completely a jet issuing out of a nozzle. And you have two Reynolds numbers. One is at high Reynolds number, both are turbulent, by the way. One is at high Reynolds number, another is also turbulent flow, but slightly lower Reynolds number. Can you guess which one of these is, medium Reynolds number, which one of these is high Reynolds number? Let us say, you can think in terms of 10 power 5 and 10 power 6 as the two values. Left one is 10 power 5 or right one is 10 power 5. Any guesses from the audience? Yeah, it's discussion time. Hello, anybody wants to respond to this?
Audience can unmute their microphone and speak to the sir.
If one of you think one is 10 power 5, other is 10 power 6, I'm asking which one is 10 power 5 Reynolds number, which one is 10 power 6 Reynolds number. Just by visual A or B kind of thing.
Right one is high.
No, one
Right one is high Reynolds number.
right one is high Reynolds number. Can you tell me why you think it's high Reynolds number flow?
It's I think its profile and the velocity at which it goes out is quite high.
Okay, okay.
Yeah.
Okay. Let us try to look at some, reasonable arguments regarding why the right one, the picture on the right, the answer is correct. The picture on the right is a higher Reynolds number, although both are turbulent flows. The one on the left, let us say, is 10 power 5, which is a high Reynolds number flow, but the higher one is on the right. We can quickly argue and look at, this is where understanding the length scales associated with smallest eddy within this particular picture on the right versus the eddy size, smallest eddy size within the picture on the left would be critical. One of the early discussions should focus on what is called the length scales. What is the smallest length scale present in the system? What is the biggest or largest length scale present in the system? If somebody looks at largest length scale, this is also called integral scale. And if somebody looks at smallest possible scale in the system, it's also called dissipative length scale, where entire dissipation happens, meaning entire energy is going to be lost. And in this context, it's extremely important to relate the link between the large length scales present in the system and the smallest length scale present in the system. How do I relate, the largest and smallest length scales? It's extremely important to appreciate something called Richardson's Cascade in this context. You think in terms of laminar boundary layer, you have a nice flattish profile. In the case of turbulent profile, you may have something like this. If you still think in terms of, several turbulent profiles, it may be another turbulent profile may be like this, another turbulent profile may be like this. As a function of time, its own, path will be very different. If somebody looks at averaging all those profiles, if you do that, you will get a nice, very reasonable looking this particular rose color, and then that will be the average. That's what engineers are concerned about. People are concerned about, do I understand the turbulence not in its actual picture but in a statistically averaged sense? Can I understand this so that I can move forward with reference to my engineering predictions? If I'm thinking of designing a pump for a 10-story building, wherein what is the volume flow rate required, what is the corresponding size of the pump that I need to install to be able to lift from a well which is, let us say 30 feet deep all the way to a 10-story building to the rooftop and so on. The question comes, is the flow laminar or turbulent, is going to decide what is the nature of pumping power requirement. This is where turbulence becomes critical. This is where turbulence plays quite a very rigorous role. If the pressure drop associated with the pump is proportional to velocity in the context of laminar flows, it's proportional to square of the velocity in the context of turbulent flows. Approximately square, but if you want to keep it very rigorous, velocity to the power 1.75. This is one of the standard textbook questions, which I'm sure the standard fluid mechanics courses would have, made all of you to study during your own fluid mechanics classes. So in terms of the nature of flow past a cylinder, for example, you can see that there is a nice Cardinal eddy shedding. You can see that these are streak lines essentially. The same shedding pattern will be very different if it is turbulent flow. You can see that although the boundary layer upstream is laminar, you can see that the downstream is so chaotic, random, disorganized. If you look at one of the snapshots, naturally you will see a snapshot like this, where the vertices are shed and and the eddies are moving forward in space and time, and then that's nicely captured. And this will give you an idea what is although the flow is highly sinusoidal here, this particular vertex street is a laminar vertex street. Please notice that they're all moving in a nice layered fashion, but then there is no intermixing. A large scale intermixing of small scale eddies is going to happen in the context of turbulent flow, which doesn't happen. It's in the context of laminar flows. Laminar flows, it's purely through diffusion. The ratio of inertial to viscous forces is the one that decides Reynolds number. If the inertial forces dominate, naturally turbulence is going to dominate. Therefore, the phenomenon is of high Reynolds number interest. So in the context of defining turbulence now, one can define turbulence as a some kind of tangle of interacting vertex tubes, and one can also go back to the Leonardo da Vinci, and he started looking at turbulence. Some of the pictures, he was sitting on the riverbed and watching the river to flow past some stones, etc., and he started looking at the nature of whirlpool that was forming. He then can be thought of as a pioneer. And you look at his hair. He said, okay, if you look at the strands of this hair, naturally you can see that the size of the hair and then the local aspects related to the rotation, etc., will also become critical. You can essentially divide these kind of bigger whirlpools, and its average can be looked at, and then one can quickly this is where high Reynolds number versus moderate Reynolds number. One of the serious things that we are interested in is if you have large scale eddies and small scale eddies present in the system. Large scale eddies are called integral scale eddies. Small scale eddies are called Kolmogorov scale eddies or dissipative scale eddies. At the level of dissipative scale eddies, entire energy is dissipated. For example, think of a family. Family gets salary, and that salary is dissipated by, by different sources. So you think in terms of source of the energy are the large scale eddies. Dissipation or its loss of energy is done by small scale eddies. The relation between the size of the large scale eddy and the size of the small scale eddy is going to decide the nature and the kind of turbulence present. For example, if the Reynolds number is very high, the smallest possible eddies in the system, you can see that pictorially it is shown here, small sizes, they are going to be still smaller. Whereas in the context of medium Reynolds number, wherein the flow is still turbulent, the size of the smallest eddy is bigger than the size of a much higher Reynolds number, wherein the smallest possible. There are two scales essentially. You think in terms of the integral scale, you also think in terms of the Kolmogorov scale. So the Kolmogorov scale is the one that is going to decide if the Reynolds number is very high or higher. So the higher Reynolds numbers are guaranteed to have much finer length scales. Therefore, if you recollect this particular picture, I said this is also high Reynolds number, this is also high Reynolds number, but this is higher Reynolds number because you have the smallest possible eddy within the system to be much finer. So the size of the integral scale eddy and the size of the Kolmogorov scale eddy or the dissipative scale eddy is going to decide the smallest possible eddy scale is going to be finer or very, very small compared to a Reynolds number which is slightly moderate in Reynolds number. So if you look at how do I kind of mathematically build that relation, That's what exactly we are going to resort to, Richardson. So Richardson gave this beautiful idea back in 1920s. He said big eddies have little eddies and they feed on their velocity, and little eddies have lesser eddies. Whirl is essentially an eddy, and so on to viscosity. When you say viscosity, this is called dissipation. This is where the entire energy is completely lost. Okay, so the large scale eddies, the integral scale eddies, can be thought in terms of are generated by the the nature of the Reynolds number, and that particular eddy is going to be having a series of continuous instabilities, and in the process of trying to pass this energy of this large scale eddy to medium scale eddies, there is no loss of energy. Please notice this. From a medium scale, you have no loss of energy, and they still become smaller and smaller, and so on. The idea is that there is a tangle of interacting vertex tubes. This is only hypothesis. So the hypothesis has has been tested beautifully, and the relations between the size of the integral scale eddy and the Kolmogorov scale eddy have been very carefully deduced. And using the hypothesis, the idea is that you have the large scale eddies in the system called the integral scale eddies. You have the smallest possible eddy scales in the system called the dissipative scale eddies. At the level of the dissipative scale eddies, the entire, maybe let me write down so that there is clarity on what we are talking about. So you have large scale eddies in the system called integral scale. You have small scale eddies in the system called dissipative scale eddies. This is where dissipative scale eddies. This is also called Kolmogorov, because Kolmogorov's Russian mathematician, essentially, Kolmogorov's scale eddies. He deduced one of the most beautiful, relations in terms of wave number and the corresponding spectrum. So that discussion may be, so let us call this integral scale eddies as L, small l, and the dissipative scale eddies as eta. If we do that, eta is just, just to give a feeling. What is the relation between L and eta? Relation between L and eta. So the idea is that the relation between L and eta, we are going to prove in a very short time. L is equal to Re to the power, eta equal to, I'm using this backslash just in the text style, length L times Re to the power, Reynolds number to the power is this caret, minus 3 by 4. So this is what we are going to prove very soon. Eta, the smallest possible eddy present in the system, is equal to the largest possible eddy in the system multiplied by Reynolds number to the power minus 3 by 4. Using very simple-minded arguments, we are going to prove this. And you will be surprised. Similarly, we can also prove the velocity of these smallest eddies and its relation to the velocity of the largest eddies and so on. The idea here is that we think in terms of the instabilities which are present. It goes purely by the stanza which was published in Journal of Atmospheric Science back in 1920s, and then this hypothesis essentially builds this kind of relation. Eta is equal to L multiplied by Re power minus 3 by 4. And then dissipation or energy loss happens at the level of the Kolmogorov scale eddies. Of course, energy is extracted by the large scale eddies, and that energy is transferred without any loss of energy to the small scale eddies. From the small to smaller to still the smallest level. Think of this. I'm not sure whether this is an excellent example or not an excellent example, but an ideal example. You have central government, which is actually, having the funds. Without any loss of energy, they transfer funds to states. Okay. From the states, it goes to districts. From the districts to mandals. Mandals all the way to the panchayats. At the level of the household, when it is actually without any loss of energy from the top to bottom, when it is transferred, and the actual dissipation or actual loss of or actual usage of that money given by the central government happens typically at the level of the lowest possible eddy scales. This example maybe can be again thought of as ideal, but that's how we want. So this is in see, without any loss of energy, there is a transfer of energy from the large scale eddies to medium, medium to small to small, on until the level of Kolmogorov eddies. There is no loss not having any loss of energy is essentially a kind of hypothesis, and that is very useful to build this relation eta is L times R e power minus 3 by 4. Okay, we'll also come back to this particular relation quickly, and then this the guy you want to salute him. He is responsible for this particular theoretical construct, and then it has beautifully survived, and there is proof for that. And then you think in terms of this particular log of the kinetic energy to the log of kinetic energy to the, I'm sorry. Yeah. If you look at the largest possible eddies transfer energy to the smaller eddies, smaller to smaller, still smaller and still smaller and so on, please look at this. This is the dissipative scale that we are talking about. And if you look at the dissipative scale eddies, this is the range over which the entire energy loss happens. Please notice dissipation is completely dominated by viscosity. Therefore, Reynolds number, if it is of order 1, entire energy is going to be dissipated. If you look at this particular picture, you have a wave number on the x-axis. Wave number is inverse of length scale, essentially. 2 pi by lambda is wave number. So lambda is the wavelength, of course. Associated with the inverse of length scale is your log of that on the x-axis and the abscissa. On the ordinate, you have the kinetic energy, log of kinetic energy. And then if you plot something like this is the kind of energy distribution present in a turbulent flow. Largest eddies will have the highest amount of energy, but they will be, without any, due to inertial influences, they simply pass on their energy to the medium scale eddies, or they just become two smaller eddies and so on. There is a kind of fragmentation kind of a process, and then entire energy loss happens only at this level is the hypothesis. Okay, any questions at this point? We can invite some questions so that people have any concerns, we can handle that. Please feel free to ask questions at this point.
What is dissipation scale?
Okay, good question. What is a dissipative scale? So, as I mentioned, turbulence has a wide range of eddies, number one. Okay, if you look at, some of that will be visible to a naked eye, some of that will not be visible to a naked eye. So, you need specialized experiments using particle image velocimetry, or you using, for example, weather. If you look at, there will be a weather pattern which is published and so on. If you look at the bigger cyclone, where you can see a big eddy, okay, that big eddy can be thought of as one possible integral scale associated with the atmosphere. But then that entire energy is also sort of, going to be distributed. Sometimes it may not be even coming down to lower scales and so on. But in the context of engineering, what happens? You have a certain large scale eddies which are locally generated. And those eddies, have energy, but that energy needs to be completely lost at some point. But because you have flow through a pipe, flow past a surface and so on, there is a dissipation associated with viscous friction. So when you have to dissipate energy, that particular dissipation is associated with the loss of energy. So the loss of energy can be thought of as a dissipation of energy, and that is nothing but the Kolmogorov scale. Okay? Any other concern?
Sir, Patnaik,
Thank you,
sir.
sir.
Good morning.
Yeah.
Good morning, sir. Hello, sir. Patnaik, sir. Good morning, sir. Hello, sir. Can I ask?
Please, go ahead.
Sir, I am Srinivas Babu from SRK, sir, Devvaram.
Please go with the question, please.
Okay, sir. Sir, my question is irrelevant to the present topic, sir. But
Then
I
we'll
have a,
after
I have
the
a doubt, sir.
after
What
the
is the difference between?
because there are 160 students who may be looking for the content rather than. We'll talk.
Okay, sir. Sir, I have a doubt. What is the difference between applied magnetic field and induced magnetic field uh, while doing problems on fluid dynamics?
Okay, we'll come back to that. So let us think of this energy cascade and the discussion associated with energy cascade. The largest eddies are created by inertial instabilities, and therefore, they rapidly break up and evolve into smaller eddies or vortices. And lifespan of those eddies. For example, what is the lifespan of a human being? Okay, lifespan of a human being, of course, with corona, the story may be different. But a typical lifespan, okay, 70 years, 80 years, that's the kind of length scale time scale we talk about for humans. So the lifespan is typically for any eddy, what is the size of the eddy? That is the length scale, okay, divided by the velocity scale. We are talking about meters in the numerator divided by meters per second in the denominator. When you have meters per second in the denominator, obviously it is time scale. Okay, L by U is the time scale. Okay, how fast is it moving? What is the size of that? Size divided by velocity is a standard measure of lifespan of an eddy. Okay, so at each instant there is a continuous cascade of energy from large scale down to smaller scales, as mentioned in the log kinetic energy versus log log of this wave number. You can see that, and then the lifespan is like this, and each instant there is a continuous cascade of energy, and viscosity plays no part in this cascade process because there is no loss of energy when it moves from a large scale to medium, medium to small, small to smaller, and so on. Viscosity doesn't play any role. There is no dissipation. No dissipation meaning no loss of energy. Energy is not lost. I gave the example of central government without any loss of energy, giving the entire funds to the states. States without any loss of energy. Of course, I'm talking about ideal cases. Don't add your own spice to this and then, do a lot of dissipation at this level. In a technical sense, there is no loss of energy is a very highly idealized settings, but at very low levels, where the Reynolds number is almost of the order of 1, there is a loss of energy, and that's what we are talking about here. Viscosity plays no part in this cascade process, but when it comes, since the Reynolds number associated with U is the velocity scale associated with the large scale eddies, and L is the length scale associated, so the corresponding divided by nu, the kinematic viscosity. You can also write kinematic viscosity as mu by rho, then it becomes rho UL by mu. Okay, so we are just talking about UL by nu is large. The viscous stresses acting on large eddies is negligible, and therefore this is also true of their offsprings. However, this entire energy cascading process completely comes to a halt, completely stops, and there is a cessation of this process once the Reynolds number is of the order of unity. Meaning, when the velocity of the smallest eddy in the system, corresponding length scale, size of the eddy, divided by the kinematic viscosity of air or water, whatever you are talking about, that particular concoction, that particular non-dimensional grouping, if it gives you a Reynolds number of order 1, order of unity, you are likely to see only loss of energy, dissipation of energy, and therefore, the size of the smallest eddies of the order of unity will do only dissipation, as pictorially presented in this particular slide. Okay. So by going with this hypothesis of Richardson, we are able to quickly derive a relation. And what is the name, what is the size of, what is the nature of that relation? We just briefly mentioned, if U is the velocity of the large scale eddies, V is the velocity of the small scale eddies, and the corresponding length scale associated with the large eddies is L. Corresponding velocity length scale associated with smallest eddy in the system is eta. We want a relation between L and eta. We want a relation between U and V. That's exactly what is going to define, how small is small, how fine is fine. So when we said higher Reynolds numbers will have always finer scales of eddies, how do I, mathematically build a relation between the integral scale and the dissipative scale? This is exactly what we are going to do. So the energy cascade process, as we said, is going to be completely dissipation free. Let us say the rate at which energy per unit mass is being supplied from large scale eddies to small scale eddies. I can write this as energy per unit mass. Let me write that. Maybe, so sorry. Energy, hello, you're able to see the screen, right?
Yes, sir.
Okay, this pi symbol is d by dt, d capital E by dt. E is energy per unit mass. Of course, T is time scale. It is simply time. I will not use the word time scale. We are using the scale associated with corresponding eddy sizes. Okay, so you want to say that pi is dE by dt. If you look at the E is energy per unit mass. You know that half mv square is essentially, energy associated with a mass of an object with a velocity v. Okay, that we are talking about kinetic energy. So if it is half mv square, we can think in terms of that energy per unit mass is half v square, and half v square is what is called, in this context, if eddy can be thought of as a single, a single concoction, you can think of its order as u square. Okay. So d by dt, the numerator here is u square, divided by denominator, change in time scale, is what is called L by u. L by u is associated with the corresponding lifespan. Okay, change in energy is d. D is the differential change in energy per unit mass. And dt, of course, is difference in time. So using this, one can quickly say, okay, L by u is the lifespan associated with the eddy. U square divided by L by u, one can quickly say it's u cube by L. Please notice these are all orders. Order meaning you think in terms of what is the size. Is it in terms of millimeters, nanometers, or meters, kilometers, and so on. So if you think in terms of that, you do not care much about the magnitude. You only care about what exactly is, is it how small is small kind of a situation. So if it is of order u cube by L, this u cube by L is essentially transferred from the large scale eddies to medium, and medium to small, and small to smaller, and so on. If you look at the nature of this discussion, so statistically under steady conditions, this matches exactly with the dissipation of energy at the smallest scales. If that is the case, pi must, this u cube by L, which is transferred from largest eddies of your system to large eddies, large to medium size, medium to small, small to smaller, and so on, must be equated to what is called the dissipation symbol is epsilon. Here the symbol epsilon is essentially trying to sort of give you, it is slightly in a tensor notation, don't care about this, but just to give you, this is essentially a strain rate. So the kinematic viscosity multiplied by strain rate 2 times is going to give you dissipation. So the corresponding strain rate is essentially velocity divided by eta. So the strain rate is, velocity gradient essentially. So velocity gradient meaning dv by dx. A typical dv by dx will give you an order of change in velocity divided by change in length scale. Okay, that change in velocity by change in length scale is what is, in a scale sense, it is presented as v by eta here. So replace nu multiplied by this nu and v, don't get confused. This is kinematic viscosity here, and this is a velocity scale associated with the dissipative scale eddies, or the velocity scale associated with the smallest eddy in the system, d by eta. So replace Sij, S suffix ij, which is the strain rate here, with v by eta. If you do that, you essentially have epsilon is of the order kinematic viscosity multiplied by V by eta times V by eta. You essentially have nu V square by eta square. If that is the case, entire dissipation according to Richardson's cascade happens when the Reynolds number associated with the smallest eddy in the system, which is called in this case velocity times nu. Velocity of the smallest eddy in the system is small v. Velocity, corresponding length scale of the smallest eddy is eta divided by kinematic viscosity. V times eta divided by nu. If it is of order 1, entire dissipation happens. If that is the case, nu v square by eta square should be comparable to u cube by L. Okay. So if that is the case, let us try to sort of build that relation. You have essentially 3 relations. Okay. Or I would put it as you essentially have you essentially have a relation which is trying to say this should be of the order epsilon. But epsilon is this. You have one relation which says u cube by L should be of order v times nu times v square by eta square. That is one relation. Another relation is entire dissipation happens only when this is true. Use these 2 relations quickly. You can write that eta, okay, here, v eta by nu, okay. So you can quickly write eta must be of the order of nu by v. Eta must be of the order of nu by, oh my god. So one can quickly say that because v is the velocity of the smallest eddy in the system should be of the order of I'm taking nu to the numerator, nu divided by nu in the numerator divided by eta in the denominator. So if that is the case, you can replace wherever you see v square, you can replace v square with nu square by eta square. If you do that and rearrange this entire discussion, you will end up getting a relation between what is called the smallest eddy size and the relation between the smallest eddy size eta and the largest eddy size within the system L and the Reynolds number. Here, please notice Reynolds number is defined as, I leave it as an exercise for you, just to deduce that relation purely using this particular version, which is equated to u cube by L, number 1. These 2 are equated, okay. Wherever you find v, you replace v here into this. You are finding v square here, corresponding v square will be nu square by eta square. So if it is nu square by eta square, it will be nu cube by eta power 4. Nu cube by eta power 4 is equated to u cube by L. If you do that and do a quick rearrangement, okay, please notice nu, we are talking about nu cube by eta to the power 4 is of the order epsilon. That is of order u cube by L. If you equate these 2, you can quickly sort of build a relation, and that relation is what is going to give you, a version like this. Eta, the smallest eddy size within the system, is going to be L times Re to the power minus 3 by 4. Similarly, the velocity of the smallest eddy size, the dissipative scale eddy size, the smallest Kolmogorov scale eddy size, velocity of that is equal to the velocity of the largest eddy size times Reynolds number to the power minus 1 by 4. Okay, ignore the ones on the right hand side. That also can be proved quickly. But then the key point I want you to notice is the following. You have relations wherein you have the largest eddy size in the system, integral scale eddy, that is called L is the size, corresponding velocity of those eddies is U, And similarly, you have the smallest possible eddy size in the system called eta, and their corresponding velocity is small b. And, yeah, I'm coming to questions. Just let me complete. I'll take up all the questions. No issue. Okay. So the corresponding relation is something like this. Here, please notice Reynolds number in this case is defined as u times L, the velocity of that divided by nu. Okay, UL by nu is the definition for, based on the largest eddy in the system, you have defined the Reynolds number here. So please notice, if the Reynolds number is very high, the corresponding eta is going to be very low because it's Re to the power minus 3 by 4. Think of Re as 10 power 5 and Re as 10 power 6. Then you can see that 10 power 6 will have a much smaller value of eta compared to Reynolds number of 10 power 5. So if you have a higher Reynolds number, the length scales, the smallest length scales possible, are going to be even smaller. If the Reynolds number is higher and higher, the smallest possible length scale in the system is going to be smaller and smaller. That's the key deduction from this, and this has been even measured very systematically. And then for example, if Reynolds number is 1000, 10 cube, based on the large scale eddies. If the size of the eddy, for example, if you have a chimney or something, chimney is releasing pollutants and so on, and one can quickly say that if the size of the chimney is 1 centimeter, of course 1 centimeter chimneys are very small, but yeah, let us say the corresponding eddy size, smallest eddy size present within the system will be 0.06 mm, because you are essentially talking about 10 cube to the power minus 3 by 4 multiplied by 1 centimeter. That will give you approximately 0.06 millimeters. So eta and V are simply called the Kolmogorov microscale. L and U are simply the corresponding integral length scale, integral velocity scales. Okay, let us now take up some questions and see the next slide also, and then take up some questions. That would be even more meaningful. Okay, so this is some feel for numbers. If you have a 100-meter tall chimney, for example, with a diameter, you would have seen lots of chimneys in industrial settings, and let us say the diameter is about 1/3 of a meter, and that it is 100-meter tall. Okay, typical velocity of the large-scale eddies. Let us say if there is a wind blowing past it, and then 2 meters per second, and then the corresponding Reynolds number is 1/2 lakh. Okay. Because it's air, and one can use velocity as this and diameter d as the length scale, and divided by nu, the kinematic viscosity of air, and one can get about 1/2 lakh of Reynolds number. Okay, so the corresponding eta here will be 0.1 mm, and the corresponding velocity will be 0.1 meter per second. One can quickly say that, okay, look, eta is L times Re power minus 3 by 4. L is what, the length scale, diameter 0.3 meters. Corresponding Reynolds number to the power minus 3 by 4 divided by the kinematic viscosity must give you a value of 0.1 mm. Okay, and similarly, if you notice the relation that was just now derived, that the corresponding velocity scale is integral velocity scale of the large eddies in your system multiplied by the Reynolds number to the power minus 1 by 4. And that will give you the corresponding velocity in this case, if the 2 meters per second versus 0.1 meter per second. Okay, and what is the lifespan of those eddies? How long will they sustain, and so on? Because these are all scaling arguments. So the lifespan of a smallest possible eddy is eta by V. We said length scale divided by velocity scale. For example, the lifespan of a largest possible eddy is the corresponding length scale 0.3 meter divided by 2 meter per second. 0.3 by 2. That will give you 0.15 seconds. So the largest eddy suffices, or its life is only 0.15 seconds. The smallest possible eddy in that system will be only 1/1000th of a second. Please see this very carefully. These lifespan of an eddy is also called eddy turnover time. So the eddy turnover time will decide, at any instant how many eddies you have in the system, what is the nature of relation, and so on. And so much of dissipation of energy surrounding 100-meter tall chimney occurs in turbulent structures which are only 1 mm or so in size. And of course, one can also, if we are simulating all this, how we should be careful in terms of resolving those eddies. See, we are talking about computational fluid dynamics. We are talking about how to computationally simulate the whole process. What is the nature of design that's associated and so on. So if we are looking at doing a full-scale simulation, we must be able to resolve a velocity and a length scale of the dissipative scale eddies. Such methods are simply called direct numerical simulations, DNS. Okay. So if that is the case, you must account for 10 power minus 3 seconds all the way to, let us say somebody is looking at a 100-second simulation or a 2-minute simulation, 120-second simulation. Then we must account the length scales all the way from 0.1 mm, meaning your grid size associated with your CFD calculation has to be that small. So what decides actually a grid size is the Kolmogorov scale eddies. Are you trying to resolve those eddies and so on? If that is the case, you must have a grid size as small as the Kolmogorov eddy size. Otherwise, for example, if somebody is thinking of catching fish, okay, the smallest fish that the person can catch is limited by the size of the net. If the size of the net is too small, okay, he will catch very, very small fish also, big ones also, and so on. Okay. If the person is trying to catch only a fish of a certain size and above, he must have a mesh size or the net size or the size of the holes of the net, the size of the holes of your fish net should be smaller than the size of the fish that you are trying to catch. Meaning the size of the fish that you are planning to catch is going to become the central, thinking in the sense of the person who is catching the fish. Okay, so in that spirit, what is the size of the eddies that you are trying to simulate would equivalently decide what exactly is the nature of simulation you are trying to perform. Are you trying to perform a simulation which includes the dissipative scale eddies, or does it not care beyond a certain length scale, beyond a certain velocity scale? If so, how do we do this? Any questions now? I think we should pause a minute and take up all possible questions and then, yeah, go ahead. Hello? Hello? Are you guys able to hear me?
Yes, sir. Yes, sir.
Yeah, please invite questions, and then there could be a lot of chat going on. I'm not checking. There are 54 chat points, and then yeah.
Participants can ask their questions by unmuting their microphone.
I'm not able to see the chat, so okay. Go ahead and.
Sir, I will read out the question in the chat.
Yeah.
Sir, how does Planck turbulence scale are different than dissipation scales? Does the dissipation scales can be related to time scales and deduce any inferences?
Not sure what the person is asking. If you're trying to say, see, dissipation is all about loss of energy. Okay, number one. So friction is responsible for all this loss of energy, number one. And if friction is responsible for this, to what extent will we be able to simulate this entire length scales and velocity scales and time scales is going to become important. If we can simulate the entire range of length scales, velocity scales, and time scales, your CFD simulation must account in terms of your delta X, delta Y, also in terms of your corresponding time scales, delta T, the time step size that one should be using has to account that level of sizes. So otherwise you will not be able to simulate the range of sizes that you are focusing to simulate. So if we are talking in the context of CFD simulations, We are yet to come to CFD, but then CFD is a sort of a discussion that's what we have sort of this entire workshop is for. So in that spirit, we may have to move beyond that and then see what we can do. Okay. So to address that specific question, I don't know what that Planck and Kerr he means. And then here we are talking about loss of energy at the level of, as expounded by Richardson, Louis Richardson. His theory is just to give you an overall feeling between the integral scale eddies. It is highly hypothetical, but one can quickly deduce what is called a simple-minded mathematical relation between integral scale eddies and the dissipative scale eddies, both in terms of length scales and also in terms of time scales, also in terms of velocity scales. All right, any other questions? Somebody was trying to ask something.
There is one more question, sir. Does these scales have any range of measurements?
I mean, that's what we were talking about. All the measurements are associated with this entire, what was that person listening? This entire feel for numbers. This entire some feel for numbers is all about that. So these are all about feel for numbers. For example, you see a big, explosion like this, wherein, some kind of volcanic eruption like this. So we are interested in looking at what is the size of the diameter of the volcanic eruption. Okay. If the volcanic eruption is of the size of, let us say, 20 meters in diameter, what is the smallest, length scale that we are going to, in terms of dissipative length scales? If L is of the order of 10 meters, and the typical turbulent velocity associated with this is 40 meters per second, if the viscosity is this, one can quickly estimate the size of the smallest eddies present. For example, one can clearly see, very close to this by zooming, and then, hey, look, I can quickly compare that with the mean free path and say, hey, turbulence is continuous and so on. So in the sense of the, relation with extremely simple-minded arguments, such as the energy cascade. For example, there is no loss of energy from integral scale to medium sizes and small up to the level of smallest possibilities. When we say smallest possibilities, both in terms of length scales and velocity scales, both length and velocity together will give you the lifespan of those eddies. How long will they suffice? Okay, what you see with the naked eye, something like this, one can quickly make an estimate. And based on that, one can say, hey, this is the corresponding, size of the eruption and so on. Okay, the energy contained by this is this, and then this can be dissipated in more time and nothing to worry, and it's not going to, result in any very serious downstream trouble and so on. Okay, so we talked quite a bit on the length scales, time scales, and velocity scales, which is critical to understanding turbulence. But then there could be lots of questions associated with this. Unless I see the people and then see them face to face, it's very difficult to make them appreciate what's going on. But the key point of emphasis is the following: in the Richardson's energy cascade, the rate at which energy is transferred, simply called rate, meaning dE by dt, energy is transferred, is U cube by L. If that is equated to epsilon times Sij, which is ratio of strain rate square times the kinematic viscosity, one can quickly build a relation which essentially shows that the integral scale, length scale, and the corresponding Kolmogorov scale or dissipative eddy scale or smallest eddy size in the system, they are connected. And that connection is what we were trying to prove as eta is equal to L times Re power minus 3 by 4. Similarly, the V, the velocity scale of the smallest eddy in the system, is equal to the velocity of the largest eddy in the system times Re power minus 1 by 4. It is only a first-hand, simple-minded argument, and we can use that information. But let us move on beyond that. You have the Navier-Stokes, and we are interested in looking at Navier-Stokes. forces on a blob of fluid and how the fluid blob is responsible for one can quickly derive Navier-Stokes from Newton's second law of motion, and one can say, okay, once we derive Navier-Stokes and what's going to happen and so on. So let us see. You have a, I mean, there are several ways to derive Navier-Stokes, but the simplest possible way one can think of: assume a fluid particle which is spherical. The size of this particle is, let us say, rho is the density of this particle, and then you can say v is the velocity of this particle going along a certain streamline and so on. One can quickly show that the mass times acceleration of this is responsible for is due to the forces it experiences as it moves. In the context of a Lagrangian, one can quickly say that if del V, which is the volume of this blob of fluid, multiplied by the density rho dV will become the mass times, of course, v is velocity. You need to look at acceleration, of course, how is it accelerating within the system, one has to look at, and it of course experiences pressure forces, which are surface forces. One can think of pressure force always as a, pressure is always negative and therefore it is inward. So assume that there is a surface pressure force acting on this, and all the fluid particles surrounding it are bombarding the surface, and then therefore there is certain pressure, and that pressure is responsible for so you can integrate that pressure and then simply say mass times acceleration of this can be written as net pressure force plus the viscous forces. So sum of all the forces on the right hand side, mass times acceleration on the left hand side, plus the body force. Body force, if the particle is suspended in the fluid in a gravitational field, and therefore you have or any field, for example, it could be electric field, magnetic field, gravitational field, whatnot, all kinds of volume based forces or body forces, all kinds of surface based forces, or you can think in terms of the pressure force, viscous force. These are all surface based forces to a certain surface, and therefore you you have surface forces plus volume based forces, body forces, and corresponding to this blob of fluid, one can write down something like this: rho dV is the mass, dV by dt is your material acceleration, or the acceleration associated with change in velocity. Capital D is specifically mentioned to make sure that you understand there is a material acceleration associated with this. The change in velocity divided by time is what is mentioned here. So you have mass times acceleration, which is equated to the net pressure force. Of course, I said you have pressure distribution on the surface, and therefore pressure is always, we said, it is inward and compressive, and therefore minus P is what we are talking about. You integrate the surface pressure all over the surface of this spherical blob of fluid, and you end up getting the net pressure force. Okay, plus the viscous forces. Of course, viscous forces are dependent on the wall shear stress gradients, and then body forces, because it's suspended in gravity. Mass times gravity is what is mentioned here. Mass is rho, and dV is the volume of the spherical blob of fluid. Okay, rho dV times g is plus the viscous forces. All right. So if that is the case, one can quickly show that this is how it is, and then one can transfer using divergence theorem. One can write surface forces, surface integral is translated into a volume integral, and then integral minus PdS is now replaced with a gradient of pressure times del V. We can cancel del V on both sides, or also write viscous forces in terms of the shear stress gradient, something like this: gradient of shear stress, delta Yj by delta Ji by del Xj, and plus rho g, and this del V is common everywhere, and then gradient of this multiplied by del V is nothing but the viscous forces, and one can cancel del V on both sides, and then sort of build a relation like this. This is how Navier-Stokes pops up. Is this Navier-Stokes equation sufficient for our understanding of fluids is a key question that one has to address, and one has to answer this, and then if that is the case, So if that is the case, the corresponding mass conservation equation, momentum conservation equations can be written something like this, the equivalent of what we wrote just now. But then here, please notice, in the context of Navier-Stokes, we start with mass times acceleration is sum of all the forces, and then we go beyond this and then look at this, shear stress, gradient of shear stress. But this shear stress needs to be written in terms of, the corresponding strain rates. That relation requires Newton's law of viscosity. So essentially, Navier-Stokes requires three principles: F equal to ma. You also require the corresponding Newton's law of viscosity. You also need to plug in the mass conservation. So the sum of mass conservation, F equal to ma, Newton's second law of motion, Newton's law of viscosity, three pieces, three laws put together is your Navier-Stokes. That version of Navier-Stokes is presented here in at the bottom. You essentially have the vector form. The one in the top is the corresponding components. Here U, V, W are the three velocity components in the X, Y, Z directions. And then one can quickly realize that this is the mass conservation applied for incompressible flows, and one can quickly see that this is your local acceleration term. These terms, all three terms put together, are called convective acceleration terms. One can quickly also see that you have a pressure gradient term here. You have the viscous force related term here, mu times mu by rho times del square u is what you see here. You can quickly see that you have x momentum conservation, y momentum conservation, z momentum conservation. In a system with three components x, y, z, you have the corresponding velocities associated with the three directions. Of course, pressure is a scalar, and therefore you only have a particular value p. So now you can see that you have four variables, u, v, w, and p as four variables. X, Y, Z are your independent variables. You think in terms of solving this, and beautifully the system can be solved. But unfortunately, for Navier-Stokes, I'm not sure how many of you are familiar, there are no closed form solutions. When we say closed form solutions, we are talking about analytical solutions. Can somebody solve this mathematically if boundary conditions are given? The answer to this is yes and no. Why yes and why no? Because many people have left. It is better to ask some questions so that we can at least face some audience. Can we go to questions, please? Even from the chat, you can also sort of.
Participants, please unmute your microphone and ask the question.
Yeah. We'll briefly pause so that they can ask questions.
Sir, good morning, sir.
Yeah.
Sir, I have a doubt, sir. I'm working on non-Newtonian fluids in
Sir,
mathematical.
let us confine to this discussion, because there could be many silent listeners who may not be,
Okay, sir. Okay.
Specific thing. Let us focus only on this. Very nice sound. Okay.
Okay, sir.
Focus on the current discussion.
Okay, sir. Okay.
Yeah, any questions? Okay, if there are no questions, we'll move forward. The Navier-Stokes equation that we have just derived requires three cardinal principles to be accounted. One is the Newton's second law of motion, F equal to ma. The second one is, of course, what you are not able to see in the derivation is how the mass conservation has been applied. And you also need to look at what is called the Newton's law of viscosity. That must be accounted. That's how there is a relation between shear stress tensor and the strain rate tensor. And typical relation tau ij is equal to gradient of the strain, gradient of velocity or the strain rate multiplied by the dynamic viscosity, mu times del ui by del xj is what is typically presented. And once you plug in that, you end up getting this complete version of Navier-Stokes. And Navier-Stokes in itself is a separate discussion. But then just to give you a quick idea, these equations technically are solvable. You have 4 equations, 4 unknowns, and the number of equations is equal to number of unknowns. It's possible to solve it in a closed form. But there is no closed form solutions except for simple cases. Simple cases, for example, pipe flow, etc. You have closed form solutions. You have flow through, between the 2 parallel plates, or flow between stellar quartzes, and you have all kinds of varieties of flows in which simplified geometries exist. And for those cases, there are certain assumptions, and those assumptions will give you or lead you to simpler solutions. But as it is, these equations are solvable in a very technical sense, but then, writing down the closed form solution and proving the global smoothness and regularity of these equations are the available solutions is one of the millennium problems called, there is a Clay Foundation. The Clay Foundation back in 1998-99, they have declared about $1 million prize for proving the global smoothness and regularity of these equations. That means there are global solutions which are universally, possible to be satisfying these equations with the corresponding boundary conditions. People are solving these equations. People are able to solve these equations in a numerical sense, meaning in an approximate sense. What is being expected from the Clay Foundation is to see whether there is some mathematician able to prove the global smoothness and regularity of these equations. Okay, so somebody who is a mathematician surely will be more interested in looking at this. So if you look at flow past a cylinder, let us say you have a flow from left to right, you have eddies formed and shed, and then one can see that you have a certain vertex street in the downstream, and these eddies, what you notice here, are going to be highly chaotic if the Reynolds number is higher. Let us assume this is a laminar vertex street and this is a turbulent vertex street. If somebody is measuring at this particular point, what is the nature of velocity variation at this point using a velocity probe? One can quickly say at some point if you measure, you will see at one instant something like this. At another realization, you may end up having like this. This is exactly what we were saying in the past some time ago. You can average all these variations and then focus only on the averaged version of this without really worrying about the turbulent nature of the flow that is present. So the turbulent nature of the flow which is present is not that important, but what is its influence on the mean flow is extremely important. If you look at the nature of this variation, you can see that there are small scale variations due to small eddies. There are also large scale variations which are associated typically with the large eddies. So this variation that I'm talking about, if somebody is looking at a variation something like this, if there are minor variations, these are high frequency components. If there are very cyclical variations like this, these are low frequency components associated with scale eddies. High frequency components are associated with small scale eddies. So it is important for us to see whether we are interested in resolving what level and scale of these eddies. So in a very strict sense, the entire discussion that we should focus on should essentially revolve around the idea of statistically averaging these equations and solving those equations in a statistically averaged sense. Rather than solving them straight away, okay, I can solve Navier-Stokes, can I jump to this? If you want to jump to solving this, your length scales, time scales, and velocity scales should be dictated by your corresponding dissipative scale eddy size in your system. The mesh resolution associated with delta X, delta Y, delta Z should be able to catch the smallest possible eddy in the system. If that is the approach you would like to follow but that requires a certain level of computing power and certain level of high performance computational calculations, which may be beyond the reach of most people. And in fact, some of these top 500.org computers are devoted very routinely for direct numerical simulations, DNS. So in that spirit, statistical averaging route is the right way to proceed, and then one can think of, if you have a turbulent flow and a non-turbulent flow, if you're measuring at various stations, for example, if you're measuring at this point, how is that velocity fluctuation? You can see this. So in a very strict sense, at this point, if you measure it, the flow is highly turbulent, it will have a picture something like this. If you go a little away, and it may have certain intermittency, you still go far away beyond this particular point. You can see that at this point, you can see there is a intermittent burst of velocities. So this entire boundary that you notice in itself is not a static boundary. Depending on the upstream conditions, this boundary could be changing as a function of space and time, and then making the internal turbulent core versus external non-turbulent, non-turbulent, mostly idealized situation outside, more of potential light flow outside. So you have a zone dominated by turbulence, you have a zone completely dominated outside, and then this interaction between the two, maybe there could be a jump between the two and so on. So it's extremely important to appreciate what exactly we are trying to simulate, and then if that is the case, one can flow past a sphere kind of a situation. You have large scale it is, small scale it is. Hey, look, I'm not interested. I'm interested in the average, time average picture of this. You may end up getting something like this. So it's extremely important to see what we are trying to simulate, and it's also important to appreciate that how do we predict turbulence, and then in the process, of course, one way to proceed for this requires, I think I'll skip this parts because it involves introduction of tensors. I'm not sure how many are familiar with tensors. If somebody is familiar with tensors, these slides, the rest of the slides would look meaningful. Otherwise, they will start shouting at me saying, let us take up some questions. I think taking up questions will be more meaningful till this point. Hello? I think I know some of the, Nagaraj must be having some question. Praveen, you have any question? Hello. I'm still not sure whether people are able to listen or they just switched on and left the place. Nagaji, how long we go? Hello, Naga.
Sir.
Naga, yeah. How long can we go? I mean,
Sir, we can go for more 10-20 minutes, sir.
10-15 minutes. Okay, sure. Maybe I think we'll go for another 10-15 minutes. But if there are any questions, I think the purpose is not to do a one-way talk. So therefore, I would suggest people should not hesitate to ask questions.
Okay, sir.
Yeah. Anything from the chat and relevant ones you can also.
No, sir, I don't find questions in chat.
Okay. I'm not sure about the background of the people. That is another reason why. Because CFD means I was thinking, mostly college faculty, and therefore.
Yes, sir, they are college faculty only.
Okay. But then they should not hesitate to ask questions because they will also know that question, whatever is the question, I think if it is relevant, not relevant, is still okay. They're most welcome to ask questions because the opportunity is to have the discussion rather than simply doing a one-way talk, right?
Sir.
Let's try to see if send link, there is a problem with the link, and I'm not sure how many. Screen is not visible. I'm not sure. Screen is not visible. Is that true?
No, sir, it is okay. It's visible.
Okay. So let us continue. Maybe I think quickly I'll try to close. These are, Navier-Stokes equations written in the tensor form. One of the important things is if the index I is repeated, that means we essentially mean this is a dummy index. And if there is a standalone index like this, it's called a range index. So in a range index, you will see that many equations. For example, in 2 dimensions, with reference to this, you will find it minus 1 by rho del p by del x1. In the y momentum, you will see minus 1 by rho del p by del x2. In the z momentum, you will find minus del p by del x3. Only one single term will be present. So whereas in the case of dummy, you essentially mean that many, you essentially mean an implied summation. For example, I is a dummy index, it's repeating. That means there is no, there is only one single equation because I is repeated. There are 3 terms here in 3 dimensions. It is del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3, okay, equal to 0. If you replace u1, u2, u3 with uvw, x1, x2, x3 with x, y, z, then you can say that it is mass conservation del u by del x plus del v by del y plus del w by del z equal to 0. That is your mass conservation. Okay, so we can expand this and then one can quickly, sort of look at the details. I think I'll skip this. So the one of the most important thing with reference to Navier-Stokes is that it's, it's quadratic in U. One of the most important aspects that we are interested in looking at Navier-Stokes, for example, let us go back to this. Here, U times del U by del X is a nonlinear term. You can say that U is actually sort of, is the velocity which is getting modified, and it's also responsible for those modifications. So in some sense, a gradient of velocity getting multiplied with velocity itself is a source of nonlinearity. You can also write this as del by del x of u square by 2 if you want. So if you do that, you essentially notice that u square is a quadratic. So essentially you are encountering a nonlinear term, whereas this term is linear term, this term is a nonlinear term. All the 3 terms here are linear terms. This is a linear term. But whereas the moment you say an unknown getting multiplied with an unknown is essentially a nonlinear term. Okay, so in that spirit, one can quickly sort of look at this discussion and realize that with reference to Navier-Stokes, you have a quadratic term in U, and this there is a complex and rich phenomenon which is responsible. Those convective terms are responsible for turbulence, and there is a mathematical difficulty in solving in the context of closed form solutions. Unfortunately, the velocity plays a dual role, and it is also the term which is getting modified, and also the term which is responsible for those changes. In some sense, U dotted with del operating on U is the one which is the convective term, which is responsible for very serious changes due to turbulence, or influencing turbulence. So steps in CFD: identify the flow domain of interest, and of course, flow domain of interest comes from a typical physical problem. If it is flow through a tube, a simple-minded flow through a tube, or a simple or a more complicated flow. If somebody is designing, let us say, a combustion chamber, the interior space of the chamber where you have an inlet port, an exit port, and you also have a piston and the bounding surface, and the entire thing becomes your flow domain. The interior domain becomes your flow domain of interest, where you have inflow and outflows for facilitating the fluid to come in and go out, and then suitable partial differential equations that describe the entire physical condition and the corresponding initial conditions and boundary conditions. That is also critical, and we need to tessellate the domain or discretize the domain, and then that is the next step. And we need to develop system of equations, which is essentially kind of translating the whole discussion into Ax equal to B kind of a situation, and solve the system of equations. Once you solve system of equations, you essentially have the vector of unknowns. Once you have Ax equal to B, typically in a CFD problem, can translate into a billion by billion matrix. Okay, n by n size will be as big as a billion. I mean, for extremely good quality computations related to engineering designs, introducing a size of billion by billion is very common. So the vector of unknowns is x vector. So that ax equal to b is the standard format in which the system of equations are generated. And post-processing is also critical. The vector of unknowns will give you certain features related to simply the velocities and pressures. The end goal may not be velocities and pressures. The end goal could be, performing your designs. How much of heat is extracted from a surface? What should be the size of the, the inlet port? Should it be bigger, smaller, and then, how do I design that? How should the design of the entry should be? And then you will look at a lot of things where you have a very detailed information available, and based on whatever is your design goal, post-processing has to be performed. If the focus is on drag, you may focus on the viscous drag and pressure drag, and then the corresponding. If the focus is on, so the functionality of the whole discussion will become very critical, and post-processing is that particular step. So I think I'll skip this. You have varieties of flows, typical shear flows, flow through a tube, and a typical bound layer, and then this is a some kind of a wake, and you can see that this is a jet velocity profile, and then this is essentially a heated surface where buoyancy driven natural convection kind of a situation, and these are all classified under what is called shear flows. So essentially we think, yeah, go ahead. Some boy question. Let's speak into the microphone, please, so that. Hello? Yeah. Okay. So statistical description of turbulence becomes extremely critical. We have briefly mentioned this. Okay? We have briefly mentioned this, but the statistical approach is to look at let us say we said, okay, you essentially have a certain velocity signal. I'm sorry, if this is the velocity signal, and it has certain high frequency and low frequency components. This is one realization. Another realization is this, and then there are plenty of such realizations. On x-axis you have velocity, time or spatial distance on x-axis, and then you are interested in looking at statistically how do I average this, and look at the influence of turbulence on the mean flow. That's exactly what turbulence modeling is trying to do. Okay, so you essentially split this mean flow or the statistical signal into two components. One is a mean flow plus a fluctuating component. The way to do that is the following. You essentially think of this as your mean, and this mean with reference to fluctuation is what we are talking about, and let us try to do that. So if you do that for every velocity signal, you are essentially, or for every variable of your system, you are dividing that into a mean plus fluctuating component. So every variable u, v, w, and p are now sliced into two parts. One is what is called a mean or average plus the fluctuating component. There is something fluctuating about the mean, and when I average all this, this is what I get. Okay, my target is this. How do I get this? To do that, I just essentially do the averaging of the equations. So once I do the averaging of the equations, the way to proceed is as follows. This was introduced by Reynolds, and it's all, one can think of time averaging, one can think of do the sampling and do an ensemble average. You have what we're talking about is an ensemble average, so that the time component is still preserved. Okay, so you think in terms of the mean and fluctuations, as I just mentioned. So if you look at this, you think in terms of the mean and fluctuation. If this is the kind of variation of any signal, it could be velocity, it could be pressure, it could be density. For the time being, you think in terms of every variable u, v, and w and p as sliced into two parts. One is mean part plus a fluctuating component. So u is u bar plus u dash. Similarly, V is V bar plus V dash. Similarly, W is W bar plus W dash. So this bar is what is called this dotted line, okay? So if I have values, it is like your class average, okay? Now somebody may be getting higher than class average, lower than class average, and so on. You just look at, a sample size of about 100 students and then look at the class average. This is the class average. I'm more interested as a teacher, what is the class average? Maybe I'm also interested in the lower performing students and extremely good performing students and so on. But then in the context of turbulence, I'm more interested in how is my average, influenced by this. So the average in the context of turbulence, the beauty is that you are more interested in the statistical average rather than the individual variations. So the individual variations would become a little bit unimportant, unlike a class 2. So you can essentially divide this into instantaneous, is mean plus fluctuating, and then you can think in terms of integrating in a continuous sense between time T0 to T0 plus capital T, average that, you get a time average. But if you do an ensemble average, you take several such realizations and do an averaging of that sample. Let us say I have another realization. At every value of time, I have, let us say, 10 or 15 values. I average all that and look at every time level. I essentially get a dotted line, and along the dotted line and how to recreate the dotted line through the simulations is my focus. So this here we are talking about sampling. Statistically sampling and averaging that sample is what we're talking about, and we can use this to be able to preserve the time component in the discussions. Okay, so if that is the case, then your fluctuating component, average of your fluctuating component would become 0, because the when you look at integral UDT will give you the U bar itself, and average of that average also will give you U bar whole bar will also give you U bar. So the difference between the two, which is essentially the sum of all the fluctuations. Look at class average is 50 marks. Somebody gets 40 marks, below 40 marks, above 60 marks. You can look at only fluctuations, plus 10, minus 5, plus 5, and so on. If you sum up all the positives and negatives, you will end up getting U dash whole bar as 0. So once you have U dash whole bar 0, one of the serious things that really influences our discussion is, okay, I can now slice every component of my signal, the velocity UVW, as U bar, the mean quantities, plus the fluctuating components, U dash, V dash, and W dash, and similarly the pressures, temperatures, and densities. And I also realized that U dash whole bar is 0, V dash whole bar is 0, W dash whole bar is 0, and P dash whole bar, T dash whole bar are 0. And I put it back, plug it back into Navier-Stokes. When I do this, I get del U by del T whole bar and average the whole equation. I end up getting, because it's a linear term, there is no problem. You get del by del T of U bar. We can prove this. There are some statistical averaging rules which have been laid out here, and one of the serious rules is this. Average of average is average itself. Sum of the two whole average is average plus the average of the individual components. And then if you have an average, treat this F bar like a constant, keep it out of the averaging process, then it becomes F bar G bar. But something like this, F bar plus F dash whole square whole bar, is going to give you average square plus F dash whole square bar. Please notice, once the moment you do F dash square bar, it's going to be positive, because minus 5 whole square plus 5 whole square will give you sum of all that is plus 25 and so on, or plus 4 square minus 4 square, 16 plus 16, and so on. All of that averaging will be non-zero. Whereas if you look at F dash whole bar is 0, F dash square whole bar is non-zero. Similarly, the fluctuation of two components, F dash G dash whole bar, is also non-zero. It's extremely important to realize this. Once you realize the story is fairly simple, you essentially translate your Navier-Stokes into, I think I'll skip this. This is about ensemble average. This is about non-stationary flow. We are talking about stationary flows here. Okay. We are talking about stationary flows, and an ensemble average will try to try to preserve this time component. So if you take several samples of this, and then if you have a tank which is issuing a fluid out of an orifice, the tank level height will reduce, and therefore the velocity keeps on reducing as a function of time. If you do many such realizations, you end up getting a time stamped simulation, and therefore one needs to preserve the time part. You cannot throw away that. So the continuity equation, the mass conservation equation, along with the momentum conservation equations, they'll be just transformed into this version, and you can see that the corresponding mass conservation will give you, I think I'll skip this, corresponding mass conservation will give you as if the fluctuating components separately satisfy mass conservation. Del u dash by del x plus del v dash by del y plus del w dash by del z is 0. This is obtained from this. You replace UVW with corresponding mean plus fluctuating. You substitute that in place of UV and W, and do a statistical average of that. And once you do that, you have del UI bar by del xi is 0, and then use 1 and 2, 1 minus 2, replace UI with UI plus UI dash, and then do a difference, and then you end up getting as if del UI dash by del xi is equal to 0. Okay. So this is about mass conservation. Similarly, we can do that for momentum conservation because that requires a little more serious discussion and a careful workout. So I'll leave the workout part because working out is not the cup of tea in a, it must be done in a classroom style, and we cannot. So if we do all that, this is what you will end up. Okay, you have the momentum. The momentum conservation equation written in a certain form here. Rho times acceleration. Okay, acceleration has two parts. One is local acceleration and convective acceleration. Then you have the pressure gradient term here. You notice that UI bar is actually the mean velocities, and P bar is the mean pressure, and tau ij laminar and tau ij turbulent, and then turbulent is the one which we are slicing in the whole process. And the moment you sort of look at this in the expanded version, you will see that these three terms, these four terms are exactly same as the Navier-Stokes equations. In fact, all these terms are same as Navier-Stokes equations, except that you had instantaneous UV, W quantities. In place of that, you now have U bar, P bar, W bar, which are P bar, and which are averaged, statistically averaged quantities. Over and above that, from the convective nonlinearity, you have the turbulent stresses or the Reynolds stresses which have popped up, and these terms require modeling. Del ui dash square by del x, del ui dash square by del x plus del by del y of u dash v dash whole bar, and so on. One can quickly write down these 9 components of stress. If you look at the 9 components of stress, and they are symmetric, this u dash v dash whole bar is same as u dash v dash whole bar, and so 6 total actual components which needs to be modeled. The moment we say modeled, we are essentially looking at approximations. Can we approximate those so that its influence on the mean flow can be obtained, and so on. The entire discussion in turbulence modeling will be revolving around how do I, solve this problem to a more meaningful problem in a more meaningful way, and can I estimate those influences of these turbulent stresses at the coming out of the convective nonlinearity, these Reynolds stresses. These are also called Reynolds stresses because it has come out of Reynolds decomposition. So the Reynolds decomposition is essentially every instantaneous quantity is replaced with mean quantity plus a fluctuating component. Once we do that, mean plus fluctuation, and we try to do the statistical averaging process, and we end up from the convective terms, from these u bar, del u bar by del x, when I wrote down this as uj times del ui by del xj, and replaced uj with uj bar plus uj dash, and ui with ui bar plus ui dash, and did the statistical averaging, something like this. And I'm not sure, unless, yeah. unless we present somewhere. I think, yeah, somewhere here, for example, f dash g dash whole bar, this kind of thing. So this kind of thing was popping out essentially to prove that uj plus uj dash, uj bar plus uj dash times del by del xj of ui bar plus ui dash whole bar will give you a term something like this. Those terms are essentially popping up as Reynolds stress tensor terms or the turbulent stress tensor terms. Yeah, somebody is writing something. Oh my God. Thank you for your writing. Yeah. So these terms are essentially responsible for the need for modeling. Okay. So the need for modeling essentially arises out of the fact that you have a convective nonlinearity. When the equations were just Navier-Stokes, you essentially have enough number of equations. Please switch off the microphone, please. Let's read this. Professor Alexa. Yeah, we are closing there, no problem. We are closing very soon. Okay. So let us try to sort of identify where is the modeling need. You are unmuted by host. Okay. So let us look at the modeling need. Modeling need is all about, you have a the Navier-Stokes equation, which is Reynolds averaged. You have the same term as del u bar by del t, uj bar del ui bar by del xj, which is the convective term. These are the local acceleration terms. This is the pressure gradient term. You have the viscous stress tensor terms. All are same as the original Navier-Stokes, but additionally you have this particular term del by del xj of ui dash uj dash whole bar, which is essentially the new term which needs modeling. If we attempt, for example, I have not actually shown the slides, but then if we attempt an equation for writing down ui dash uj dash whole bar, we are going to have higher order terms like ui dash uj dash uk dash whole bar. If with lot of energy, if I try to generate an equation for ui dash uj dash uk dash whole bar, I will have terms which are containing unknowns such as ui dash uj dash uk dash ul dash whole bar. I have not shown this part, but those who have done a course on turbulence will surely appreciate the fact that you have higher order terms. If you see very carefully, you have in this equation, you have only originally ui bar, uj bar kind of variables, which resulted in second order terms like ui dash, uj dash whole bar when we performed statistical averaging. We always have more number of unknowns than the number of equations when you do statistical averaging. Non-statistical approach to Navier-Stokes is perfectly deterministic, but statistical approach to Navier-Stokes, closed form solutions or closed set of equations becomes very difficult because you have essentially 4 variables in the form of u bar, v bar, w bar, p bar, plus 6 additional unknowns in the form of ui dash uj dash whole bar. Ui dash uj dash whole bar is essentially a matrix of values. If you think of I and j as combinations, you think in terms of a matrix of values, something like this. You think in terms of generating okay, u dash square bar here, u dash square. I can't write this easily. Okay, you can write ui dash square bar along the first row, u dash v dash whole bar in the first row, u dash w dash whole bar in the first row. Second row will be u dash v dash whole bar, v dash square whole bar, v dash w dash whole bar. Third row will be u dash w dash whole bar, v dash w dash whole bar. The last term 3 by 3 within that third row will be w dash square whole bar. You have a matrix of values which are, it's a symmetric matrix. You have essentially 6 unknowns in a 3 by 3 component matrix. So if you have 6 unknowns plus these 4 variables which are 10 unknowns, you can say that you have 10 unknowns and only 4 equations. How do we solve this? Therefore, statistical route to Navier-Stokes We cannot find a closed set of equations which describe them. Of course, single point, 2-point closures, we'll not talk about that. But the key idea here is in direct numerical simulation, in the context of wave number space, you simulate the whole, and you are also concerned about higher wave numbers referring to dissipative scale eddies, and then you essentially simulate all the range of eddy sizes, and therefore you think in terms of direct numerical simulation, very expensive. Okay. Then you have RANs on the other end of the spectrum. You average everything. You don't care about dissipative scale eddies. You don't care about integral scale eddies. But influence of those integral scale eddies is what you will be performing. That's what is called Reynolds average Navier-Stokes equation. You model everything. You don't care. For example, if you think in terms of a simple-minded velocity variation as a function of space, we said, okay, I have this kind of a variation. This variation is actually retained in this. Whereas this RANS simulation doesn't care about all that. It simply says statistically averaged is what is of interest. So in an engineering sense, a statistically averaged is what we want. We don't care about every bit of all these variations and then how those variations are influencing the mean flow, etc. But there is also in between RANs and DNS is called large eddy simulations. You essentially model the large scale eddies, model the eddies which are the dissipative scale eddies and closer to the dissipative scale, and essentially exactly simulate the large scale eddies. Large eddies are simulated. The moment you say simulated, we are referring to getting them exactly. The moment you say modeled, that means we are approximating something. The moment we model something, okay, shortcut, you can take this. For example, in an engineering sense, we can say, okay, let us try to solve everything using simple-minded correlations. That's an extremely crude model. Correlations are essentially crude models. You conduct experiments, generate a crude model, and you are happy with it. You have nothing to complain. But a little bit higher in the hierarchy is RANs. You model all the scales of eddies and a little more detail associated with what is happening near the inlet port, exit port, should I give a certain angle, etc. Can be thought in terms of a combustion chamber design if you're doing RANs. You want much more very clear details, you can indulge in LES, which is more expensive, a little more expensive than RANs. Correlations are simple-minded experiments, and you build correlations, relation between this variable and that variable, and generate a nice, simple-minded relation, such as, for example, the Hilbert's equation or Dittus-Boelter equation, that sort of a thing. So correlations are extremely critical in the context of engineering. We have been living on the correlations extremely well. Whereas RANs is a kind of, that's where most CFD packages will focus on. LES is a little more expensive than RANs, but then, it simulates large-scale eddies, but models the small-scale eddies. Then when it comes to DNS, it simulates all the range of eddy sizes, and therefore extremely expensive. You require high-performance computing because you are trying to even catch the smallest possible eddy in your system. For example, if somebody, coming back to that fishnet example, if you have a fishnet which is very small in terms of the whole size, you will catch everything. But somebody would say, can you sell all that? It's of no use. You fellow, you are an idiot. You are trying to catch everything, then you have to separate all that, and then sort of unnecessary, right? So in that sense, a DNS is extremely expensive, and then whereas RANs is an extremely beautiful way to solve our engineering problems. It's a little surely more superior than correlations. LES is more superior than RANs in terms of the computational hierarchy. This is how it goes. Least expensive, most expensive is DNS. In terms of the accuracy, again, most accurate is DNS. Very crude is correlations. Okay, that correlation may be valid in a certain circumstance, it may not be valid. Trans is a reasonable via media for engineering purposes in some sense. So mostly people are now around LES and trying to sort of simulate the large eddies accurately, and then model only a certain part of the eddy sizes which are closer to the dissipative scale eddies. In some sense, the entire story revolves around this idea of how to model, etc. We have not discussed some of the models such as K-epsilon model, Reynolds stress models, etc. are very popular, and then K-epsilon is one standard model which some of you may be familiar, and if there are questions we can elaborate on that.
Yeah, sir. Good afternoon, sir.
1 minute, I'll just put the concluding slide and then we can quickly go to all possible questions, no issue.
Please.
So the conclusions are fairly simple, and I'm trying to say, hey, look, a statistical route to understanding turbulence is one good way to study turbulent flows. RANS and its modeling is suitable for performing engineering designs, and CFD will aid the analysis of such intricate engineering systems. DNS is good but extremely expensive, precisely because it simulates all the scales present in the system, whereas RANS on the other hand does modeling of the entire range of scales. It doesn't care about integral scales, it doesn't care about Kolmogorov scales. Yeah, I'll stop here and take up questions. Please feel free and go ahead.
Yeah, good afternoon, sir.
Yeah, go ahead, please.
Sir, when you do the simulation of CFD, sir,
Yes.
the inlet velocity is within the limits of the laminar flow. Let you take the 1000 inlet Reynolds number.
You can also have a measured turbulent velocity profile. You can also give.
No, so my question is not yet completed, sir. I was operating the system with a Reynolds number of 1000. Based upon the fluid properties and the duct diameter, I calculated the velocity, and I was given the velocity at the inlet.
Okay.
Now I am assuming the flow is the laminar flow.
Yes.
But when you take the contours or vectors at certain location within the domain, it seems to be turbulent nature. Then how we can climb in such a way it is the laminar, even though the inlet conditions is laminar,
Okay.
but at certain location it seems to be turbulent nature.
I understood your question, and then if you go back to one of our slides, I'm trying to relate to my slides rather than going into the specifics of your problem. If you see the nature of discussions, for example, you can see and for an outsider, this particular shedding process may look like a turbulent flow, but it is not turbulent flow. It is a kind of Kármán vertex shedding, which is laminar vertex shedding. Vertices are shed. There is a temporal feature where there is unsteadiness. There is a certain sinusoidal feature, but this is not turbulence. Please notice, an unsteady feature like this cannot be misunderstood as turbulence, for example. Whereas if you measure the velocity at this particular station at any time, as a function of time, I may have a certain variation which will look like this. For example, if I try to measure nice sinusoid, I may see, and that is not turbulence, obviously, if I try to measure at this location. Okay, one can say, okay, it is unsteady laminar flow. Unsteady laminar flow is not turbulent flow. Whereas if it is random, chaotic, and completely unpredictable, but its average is predictable, then you can say, okay, that's a turbulent flow. Okay, coming back to your specific question in the context of CFD, you are giving some inlet velocity profile, which is laminar. And have you looked at this, whether the flow is laminar for that Reynolds number or not? If it is a pure duct flow, how are you, what kind of velocity vector contours and what location you are talking about? Because I'm not familiar what exactly you are actually, referring to in your context.
Yeah, yes, sir. We have taken the contours vectors. The vectors are just like what you have seen here. The vectors are like that.
You are referring to, and I do not know what is expected there. And then unless we see the specifics, it's unfair to respond. That's why I was asking people to stick to the discussions that we had in this presentation.
Thank you, sir. Thank you so much.
Yeah.
On behalf of Bharati Vidya Mandali and all the organizing partners, and on behalf of all the participants, I thank you very much for sparing your valuable time for us and for educating us on this particular topic, sir. Thank you for your elaborate session, sir. Thank you, sir.
Thank you, Naga. All the best to the participants. Thank you for this opportunity, and all the best. And please go for maybe lunch. I'm sorry we got delayed badly.
It's okay, sir. It's okay, sir. We feel it. Thank you, sir. I request all the participants to participate for the second session of today by 2 o'clock.